Okay, so in the previous section we saw the method to calculate the value of a second order, that is a 2 by 2 determinant, and also for a third order, which is a 3 by 3 determinant. And it came with those weird formulas. So the first term is positive, then the second term is negative, and the third term is again positive. And you may be wondering, where does all that come from? And so to look at that, we need to learn two new things. So the first one is called as the minor of a determinant. And basically, in simple terms, the minor of an element of a determinant is found out by removing the row and column of which the element is a part. And what I mean by that, let's say you have a third order determinant, A13, A21, 22, 23, 31, 32, 33. So then to find the minor of a specific element, let's say minor of A11. So I'm trying to find the minor of A11. Again, the idea is you mentally block off this row and you mentally block off this column and take the remaining part of the determinant. So that gives you A22, 23, 32, 33. Similarly, if I ask you, let's say for example, what is the minor of A23, and you write that, since we are talking about minor, it's with an M symbol, so M23, and the indices correspond to the element A23. So you block off this column and this row mentally, and you get A11, A12, A31, A32, and so on. So you can find out the minor of every single element in this determinant. The second thing that we need to learn is the cofactor of an element. And the cofactor is written as Cij for an element Aij is given by -1 to the power of I plus j times the minor of that element, Mij. And you can probably already guess what this has to do with the way we calculated the value of the determinant, because you can see that depending on whether I and j are odd or even, this sign will change from being either -1 or +1. And so the value of the determinant in general form can be written as the summation j running from 1 through n A1j C1j, and this is without loss of generality expanding by the first row of the determinant. And you can already see that for a 3 by 3 matrix, the signs of the cofactors are this pattern. So plus, minus, plus, minus, plus, minus, plus, minus, plus. And if you remember from our previous section, when we expanded the 3 by 3 determinant by the first row, we said the first term had a plus sign, the second term had a minus sign, and the third term had again a plus sign. So that is where the expansion signs come from. And this is also the way to calculate the value of any general order determinant. So this formula holds true for a determinant of order n, where n can be anything from 1 to whatever, however large a number you want. So now we need to take a look at some properties of determinants. What are some useful properties? Well, if you take the transpose of a matrix, of a square matrix, and take its determinant, then the value is unchanged. So let's say determinant of A transpose, which you can write as A transpose, equals determinant of A, or simply this. Then the second property is if you interchange any two rows or any two columns of the determinant, then the value becomes negative of the original value of the determinant. So let's say, for example, A equals A11, A12, A13, A21, A22, A23, A31, A32, A33, and then B equals A31, A32, A33. So what I'm doing is I'm flipping these two rows, keeping the middle one the same. Then, and you can check this for yourself, determinant of B is negative of determinant of A. And a corollary of this result is that if two rows or columns of a determinant are identical, then the value of the determinant is 0. The third property that we need to look at is scalar multiplication. So what happens if you multiply a determinant by a scalar? So C times A has the same effect as multiplying any one row or any one column by a scalar. So let's say if A is a 3 by 3 matrix, so A11, A12, A13, and you can multiply, let's say, the second row by this scalar, 2, 3, and the third row remains the same, 3, 1, A32. Or you could multiply any column by that scalar. Which means that you can also break down a determinant into two or more parts. So let's say if you have a determinant composed of parts such as A11 plus B11, A12 plus B12, I'm sorry, A21 plus B21, A31 plus B31, and then A12, A13, A22, A23, A32, A33, and you can decompose this into two determinants equals A1 plus B1, and as you can probably guess, A1 would be A11, A12, A13, A21, A22, A23, A31, A32, A33, plus the second component, which is B11, B12, B13, and these two columns are the same, so A12, A13, A22, A23, A32, A33. So this is a way to decompose a determinant into two or more parts. And then one last property is that if the elements of a determinant are polynomials in a variable, let's say x, and then so let's put this down. If elements of determinant are polynomials in x, and you can find out that if the value of the determinant is 0 when x equals a for some value a, then you can be sure that x minus a is a factor of the determinant a. For example, if you have a determinant a such as x, y, z minus yz minus xz minus xy x square y square z square, using this rule, you'll find out that this can be factorized into x minus y, y minus z, z minus x, and xy plus yz plus zx, simply by cyclically substituting x for y, y for z, and z for x. Okay, so those are the important properties that we need for determinants in order to be able to work with them. And let's for a moment step back to matrices, as we still need to consider some special types of matrices. I'm going to put a line down here, and let's take a look at special types of matrices. So the first special type that we need to consider is a symmetric matrix. And a symmetric matrix is defined if A equals A transpose. This only works for square matrices. So for example, if A is written in the general form Aij n by n, if Aij equals Abi for all ij, then A is called to be symmetric. Then we have anti-symmetric. Some people like to call this as skew symmetric. They both mean the same thing. And the definition of this is if A transpose is negative of A. Again, this works only for square matrices, and the condition for that is Aij equals minus Aji for all ij.